Hey, Ruben. How's it
Hi.
going?
I'm very stupid. I had set that upside down. Okay. All right. I'll try and write a bit bigger than that. But
Oh, by the way, Ravin, you can pin your video because it's recording, right? So we
yeah.
in the recording we'll see your screen.
So yeah, it is pinned. Oh well. Yeah. So that should be fine. So welcome to Consultation. How can I help you?
I just have a quick question regarding the assumed knowledge, just relating to my email last night. Mine will take 2 minutes, and if that's okay. So so the things I didn't cover in 9024 are heaps / priority queues. I'm assuming they're the same thing with the slash.
Yeah.
Hash table and sorting algorithms. So I taught myself merge sort last night. It's pretty easy. With heaps, well, I understand what a heap is. I read that, but then there are all these algorithms associated, like max heapify, build max heap, heap sorts.
Right.
So is it everything about heaps we need to know, like all these algorithms as well, or just what a heap is?
So you don't necessarily need to know all the details of those algorithms. You should have an understanding of the basic principle. So the idea is, for example, when we talk about heapify, the idea is that we can, if the heap property, which is that in the case of a max heap, the parent compared to, say, 2 children.
Right.
In a heap, in a max heap, the parent should have greater value than both the children, right?
Right. Yeah.
The idea is with heapify that we can correct this property by kind of bubbling up, bubbling down. So if I were to change the value of C2 to, by increasing it, then if necessary, I could swap it with its parent. So for example, if I have, let's drop an example. A heap like this, right? A max heap. Right. Note the contrast between a max heap, which is itself is a binary tree in this case, as opposed to, say, a binary search tree where we're guaranteed that the nodes are in completely sorted order.
Yeah.
In a max heap, we only have partial sorting, right? We have partial ordering of the entries. We don't know relationships between things in different subtrees, subtrees, but we have orderings down any path.
Okay.
Now, the main principle is that heaps allow editing individual entries in order log n because they have height log n. And if we change this value 8 to, say, 15, which is bigger than its parent, this is now no longer satisfying the heap property. And we correct that by comparing it with its parent. So because it's the new value of that child, 15, is bigger than the value of its parent, we can bubble it up. And one of the properties of the heap is that we're guaranteed that when we replace this 10 with the new value of the child, 15, well, that's only increasing it, and so we don't even need to look into the subtree at all.
Okay.
If 10 was bigger than everything in that subtree, then certainly 15 will also be bigger.
Yeah, I see.
But now that we have a 15 here, we again need to compare it against its parent and so on and so forth.
Yeah.
So so if you can, the point is not to memorize the implementation details of all these algorithms, but to understand the principle that we can rebalance heaps and we can edit individual entries of heaps.
Okay, so I'll go over those. So just about, will you be able to kind of revising the stuff as we go along, or is it just make sure if you don't know the stuff, you know what I mean?
Yeah, I understand. See, here's part of the tricky part of it. There's actually going to be more reliance on the assumed knowledge now than later in the course, if that makes sense.
Okay.
Because later in the course, we will introduce some ideas of greedy algorithms, dynamic programming, max flow, etc. And those things you can, those things we will introduce mostly from first principles. There might be times when we plug in a piece of assumed knowledge. So for example, there are some greedy algorithms that use heaps, like Dijkstra's algorithm, which you might be familiar with. But we will build some of that. We will, like, the new material in the course will be built up as we go, right? Whereas in week one, when we're trying to give you some work to do, tutorial exercises and assignment, then we haven't had time to teach you much yet, and so we rely on the stuff that you've seen in previous courses, and everyone's a little bit rusty on some of that, so it might be a little bit of a struggle to recall or fill in the gaps in your knowledge, and we understand that, but it will get easier in that.
Okay, that's great news. Okay, sorry, last question. So hash tables, I assume there's
however, I will just mention that's not completely true of the mathematical prerequisites. Those will be quite necessary in about week 3 or so of the course, where we talk.
Honestly, I'm actually a pure maths patient. I studied pure maths in my undergrad, so
beautiful. You'll be fine.
I'm not worried about the maths. It's just the computer science assumed knowledge.
Yeah, so that's certainly not the case for everyone. So for the rest of you who are in the consult right now, yeah, there will be some heavy duty mathematics around week 3 or so. It is not the main focus of assessment, but it is thematic. It's illustrative of some of the concepts, and that's why we include it. We will not be I'll be very clear about expectations of what you're meant to reproduce as opposed to what you're meant to take away in terms of the moral of the story. Okay. However, the lectures will be difficult to follow at times if you don't remember, for example, what complex numbers are and how to multiply them. Then it will be quite difficult to follow, like FFT, which unfortunately is just how it is.
Okay, so basically just have an okay understanding of these concepts. Just not rigorous, but like understand. Like I should be able to repeat the algorithm without formally reading.
More than being able to repeating the algorithm is good. We are more interested in, you should know the properties of the data structure. So you should know that, an example is the hash table, which we were talking about in the P tutorial just now. Rather than remembering the implementation details and so on, and we'll touch on this slightly when we get into the string matching topic very late in the term. But the main idea is you should know that the most famous operation, at least, of a hash table is that you can look up entries in expected constant time.
Okay.
That's more important than knowing exactly how to build one.
I see. Okay. Thanks, Raveen.
Okay.
Yeah, someone else can go.
Okay, great. Yeah, sure. James asks, can you explain why the cost for merge sort is n log n again, please? I get log n binary search bit. Okay, so merge sort sorry, let me just organize my things. Merge sort said, say I have an array that's of size n. The way I'm going to sort this array is to break it in half into 2 pieces of size n over 2. I will recursively apply the same algorithm. So I'll apply merge sort to the first half and merge sort to the second half, and then I will merge them together into a single array. The idea is once these 2 subarrays have been merged using merge sort, I can compare the first entry of this one with the first entry of this one. And for example, if this one is smaller, then this one goes into the first entry of the merged array. We'll advance our counter in the first half and compare our new 2 active entries. Say if this one is smaller, then this one will go into the second slot of the merged array, and so on and so forth. Again, advancing the counter through the second subarray. Now, the easy explanation of why merge sort runs in order n log n is to work out where the actual where the runtime comes from, what operations are costing us runtime. The splitting is more or less free, right? You can split something and it's not particularly costly. But the merging actually requires work. So how much work is it actually to merge two arrays? Well, if I have an array of length half n and an array of length half n, to merge them takes about n operations, right? Because we are comparing pairs, and we'll do one comparison for every new array element we get. Because again, this one required one comparison, this one required one comparison, and so on. So we'd expect that constructing the merged array takes order n time. And that is exactly the sum of the two subarray lengths. Now, the important part is this is a recursive algorithm. So let me make sure that I set this up properly.
We can't see what you're writing now.
Sorry?
Oh, we can't see what you're writing now. I think the camera angle.
Yeah, I'm gonna
Yep.
put it back there. Okay, so let's just, there we go. The array of length n is getting broken down into half n's, and so on and so forth, right? This paper is, this ink bleeds more than bleeds through the other side more than I anticipated, but hopefully it's still clear enough. So the splitting, as we said, costs a negligible amount. However, it's the merging that's important. If in the, say, fourth level down, each subarray is of, sorry, let me just point out first that this goes on for log base 2 of n levels, because we halve the length log base 2 of n times until we get to individual numbers, right? Also, in each level, we should think about how much work was it to assemble each of the sorted arrays at that level. So for example, in the third level, there are four subarrays of each of length n over 4, and it took n over 4 time to merge their two children, right? This merge operation took about n over 4 operations because we were merging two subarrays of length n over 8. What's more, if this one takes n over 4, then so does this, so does this, so does this. And so the total work to do all the merges in the third level is order n. And the same is true of the second level. If we're merging an n over 4 with an n over 4, that takes order n over 2 time. And again, n over 4 with an n over 4 takes about n over 2 time. Together is order n. So we end up adding log base 2 of n terms, each of which is about n, and we get order n log n in total. So yeah, each comparison is one fundamental operation. At each level, there are approximately, up to us, some of the final entries in the merge don't actually require a comparison, but we can we can safely assume that there's not many of these. So in every level, we require about n comparisons, and there are log base 2 of n levels. So does that clarify?
So would you say so it's the splitting is log n. So would you say it's O log n plus n log n, but then O will come down to n log n?
So yeah, if each splitting operation takes constant time. Oh wait, sorry, let me rephrase that. Yeah, so you can actually prove with a little bit of thought that there are a linear number of subarrays in total, right? Think about it. There's about 2n subarrays if you're precise with it. However, any constant amount of work per subarray, just like to define the subarray, to like set its endpoints, would come out to be a linear amount of work overall, and this is dominated by the n log n that we've derived already. So where we have time complexities that look like order fn plus gn, if it happens that fn is much bigger than gn, then we can essentially ignore the gn. And we'll talk about this in more detail in the next lecture.
Oh, so it's not log n, but it's like linear 2n.
So for example, if I have a expression that looks like this, n plus log n, then this is actually this can be simplified to just linear time. And the reason is that the log term is much smaller than the n. Again, we will talk about the specifics of what exactly this bigger notation means. We'll talk about that tomorrow. So perhaps that will clarify things. Does that?
Yeah, that makes sense. I'm just asking the splitting part. Did you say it was 2n instead of log n?
So there are 2n. There are about 2n subarrays. So 1 in the first level, 2 in the second level, 4 in the third level, and so on. And assuming a constant amount of work just to work out the midpoint each time, that would amount to a linear amount of work across the entire problem. But when we add that linear amount to an n log n, then the n log n dominates. So we can ignore the linear term in the statement of the time complexity.
Yep.
Does that clarify? If you have n log n plus n, well, the n doesn't matter next to the n log n, because the n log n is asymptotically bigger.
Yep, got it. Thanks.
Okay, cool. Further questions?
Yeah, so like you recommended using this textbook, right?
Yes.
How do we do we use it as like a reference guide, or do you suggest that we attempt the problems in it as well?
So of course it will depend on your individual circumstances. I understand that not everyone has ample time to do more supplemental work. Anything that you can do with the textbook will be beneficial. If you read the textbook, it will hopefully give you a better understanding of the lecture material. I would hope that the lectures are self-contained, but of course the textbook will elaborate on things. So perhaps at times the textbook explanation might make more sense to you than what I say, which is fine. In addition, one of the things that we're going to keep repeating throughout this course is you have to practice. You have to do lots of practice problems. The tutorial exercises are one source of that, but there are exercises in both textbooks which may be of interest to you as well. Does that answer the question?
Yep.
Okay. James asked for 1 or 2 problems from the tutorial sheet. I'm happy to do that. Does anyone have a suggestion? Question 6, sure. Okay. Okay. So let's understand the problem first. So in an array of 2n elements, we want to find the max and min with up to 3n minus 2 comparisons. Oh, I'm slightly out of frame. Let's go with that. So we have an array of 2n elements. We want to find the max and the min of the array with up to 3n minus 2 comparisons. And how do we do this? So I'll see if I can get to 7. Yes, you will get the answers to the tutorial problems later. We don't want to give them away right now because it will spoil the questions for you. It's a bit like when you have a textbook that has the answers in the back. That I feel like that discourages you from letting the problem sit with you for a while. And if you can always flip to the back end, it doesn't really train you to solve problems. It trains you to read and understand solutions to problems. So you will get answers, but not right away. Okay, let's first establish, does the obvious solution work? And if not, why does it not work? So what's the most natural solution? Find the max and the min separately, right? So how many comparisons does it take to find the max in an array of 2n elements? Yeah, it should take about 4n in total because the max takes 2n and the min takes 2n. Now, we should note here that the problem is written, like the solution refers to 3n minus 2, so we should be a bit more precise. We should try and count the exact number of comparisons. How many comparisons do you need to find the max? You're going to start by comparing the first 2 elements and keeping the greater of them. Compare that with the third element, keep the biggest one, etc. And so we get 2n minus 1 comparisons. Now, if this was part of my actual solution, then I would write a bit more explanation of this, but hopefully it's clear why this is why this is not good enough. Yeah, sure. Why is it 2n minus 1 in more detail? Absolutely. So if let's look at an example. 1, 3, 2, 4, 5. If I want to find the max, I'll first compare these two, and I'll get 3. Next, I'll compare the better of those two with the best so far with the next element, so I'll get 3. Then I'll compare the best so far with the fourth element and get 4. Then compare the best element so far with the next one and get 5. In this way, we were able to find the max of an array of length n with n minus 1 comparisons. In our problem, the array has length 2n, so it will require 2n minus 1 comparisons. Yeah. We'll detail this a little more when we're actually writing it up for real. Yeah. Okay, so we need something better than this. And here we have to be a bit creative. Yeah. So how could we cut down the number of comparisons? Because the idea is that maybe there are some comparisons that are repeated, or some comparisons that are redundant if we look for the max and the min separately. Maybe we can do some pre-processing that lets us find the max and the min, or narrow down our searches in a faster way. Kaya suggests keeping track of two variables, max and min, so the max so far and the min so far, and do it in one sweep. Let's see what happens. So I'm going to keep a tally of the comparisons that we use. So first I'm going to compare 1 and 3. So that's going to be one comparison. And I'm going to keep track of the min the max so far, which I'll write down as 3, and the min so far, which is 1. And we were able to get both of those with one comparison. So that's good. Actually, let me just bring this up to be an even number so that we have a direct analogy to the question. Okay, next we are going to compare with the new number 2. However, that new number has to be compared with both the max so far and the min so far. Right, so to find the new max so far, we need one more comparison, and to find the new min so far, we need another comparison. Do we agree? Don't know what that is about. Okay, next we're going to compare with 4. Again, we need to compare 4 with the current max to get 4, and we need to compare it with the current min, which is still 1. Next, we compare 6, and that's another 2 comparisons. And now we compare 5 with the current max and the current min, another 2 comparisons. This took 9 comparisons. Our previous approach took 4n minus 2, which in our case, where n equals 3, is 10 comparisons. So we reduced from 4n minus 2 to 4n minus 3. Really, all we saved was one comparison, because the first pair of current max and current min can be found with one comparison, but every subsequent pair still require every subsequent array element requires 2 comparisons. So we're still out of luck. Yeah, so so I guess one way that I might explain how to make some progress here is, in our proposed solution, we are checking every element for potentially being the max and every element for potentially being the min in both the solutions that we've talked about. So is there a way to narrow down, to categorize first some elements as being potential maxes only and other elements as being potential mins only, so that we don't have to then compare each of them to both the max and the min? Yeah, can you bucket these array elements so that only some are considered as candidate maxima and some are considered as candidate minima? J, order them as you compare. Ordering, you're starting to get into sorting territory, which again has like n log n ideas. James says, if the max is changed, don't compare the min, or vice versa. That's a good idea, actually. However, I'm not going to go through the details. I can tell you that that's in some cases, it will achieve 3n minus 2 comparisons or less. In other cases, it won't. So unfortunately, while yes, it will solve some cases, we need a solution that works in the worst case, no matter what array we're given. So you can come up with a counterexample, perhaps. Try and invent an example where your an example array where your scheme takes more than 3n minus 2. Jaden has a great idea. So here's the thing, the hint is kind of in the question. The array has 2n elements, and that's a rather odd thing to specify, right? Usually arrays have n elements. There being 2n elements is indicative that there might be some benefit to pairing the elements of the array. Now, yeah, Jaden is exactly correct. We are going to pair off the array elements. Group the array elements into pairs. So we'll do A1 and A2. All the way up to A2n minus 1 and A2n. All right. Each of these can be compared, each of the pairs can be compared using one comparison. We can designate the smaller value as a candidate minimum. And the larger value as a candidate maximum. So far we have used n comparisons. So I'll just keep track of that. We have used n comparisons so far to isolate which is the bigger and which is the smaller in each pair. Now you should, there should be a little voice in the back of your head saying, what if they're equal? If two entries in a pair are equal, then we can assign them arbitrarily as candidate max and candidate min. Of course, neither of them will be useful. You can convince yourself, I hope, that it doesn't matter which one is which, right? If they are equal, designate arbitrarily. They are equal values, so we can just as easily make one of them bigger and one of them a big one and one small one. Okay, so we got that so far. We have these n comparisons to split them into pairs. Now, we have n candidate maxima and n candidate minima. Just positioned. Okay. How do we isolate which of the candidate maxima is the actual maximum and which is likewise the minima? It will be the same algorithm that we've talked about before. Just scan through and keep track of the maximum so far. To find the maximum, And because the array of candidate maxima is of length n, then we only require n minus 1 comparisons. We can say similarly, the minimum is found in a further n minus 1 comparisons. Therefore, we find the maximum and minimum in n plus n minus 1 plus n minus 1, which is 3n minus 2 comparisons. Now, I'd say that this is not a complete submission, for example, if this was an assignment problem, because there's one, I've certainly found an algorithm and I've justified why it achieves the stated number of comparison operations. But there's one thing I haven't really justified or explained as clearly as I'd like. And that is, I've only found the maximum of the candidate maxima. I should explain I should include an explanation of why that's enough to actually find the maximum in the entire array. And for this, I should explain why none of the candidate minima are eligible to be the actual maxima of the maximum of the array, right? Why is it enough that instead of searching for the max in the entire 2n, why is it only enough to search among the n who were the better of their pairs? And of course, this is fairly simple. It shouldn't require much justification. Note that the must be greater than or equal to, I'll write it in words. All other array elements. So in particular, it is greater than or equal to the other entry in its pair. And therefore, it is guaranteed to be among the candidate maxima. The same applies for minima. Right. Oh, right. Yep. So yeah, note that the overall maximum must be greater than or equal to everything else in the array, and in particular, greater than or equal to the other thing in its pair. So that means that, yes, the actual maximum does appear about among the candidate maxima, and therefore this justifies the correctness of our algorithm, as well as we talked about, the number of operations. Kai says, would you say this is divide and conquer? I would not describe this as divide and conquer, and for a particular reason. Divide and conquer refers to algorithms where we split the problem into identical but smaller in size subproblems, right? In this problem, we are not splitting into identical subproblems. We are splitting into kind of case 1 and case 2, right? Because we are not solving the same problem, that is, find the max and min of a smaller array. Incidentally, if you were to find the max and min of a smaller array, that's a divide and conquer approach to this problem. And I'm not sure off the top of my head whether you could arrive at a complete solution, but yeah, Hannah, that's perfectly fine as well. You could explain that none of the candidate minima can possibly be the overall max. That's perfectly fine as well. Do you want me to write that, or is the question, would such an explanation be acceptable? Okay, cool. Yeah, so absolutely that way of writing it is just as valid. Yeah.
Hey, Ravine. I'm not sure if I have one super quick question, sorry, regarding heaps. I'm just reading over it now, the content.
Yep.
I'll quickly share my screen.
Sure.
Sorry, could you enable screen sharing? Because I've just got the PDF of the book up, the algorithm design book, sorry.
So is this Charlie speaking?
Yes, Charlie, sorry.
Yeah, no, you're right. I just need to work out how exactly to.
So you finished that previous question, right? Oh yeah.
Does that work? Are you able to screen share?
Okay, so you can see me.
Because my video is pinned. That's probably going to be a problem.
The host disabled attendee screen sharing.
If you go to security and enable screen share for participants, that'll work.
It's in security, isn't it?
Yeah.
Okay, there we go. Okay, that works.
Yeah, that works. Thanks.
Okay.
So just with heaps, basically when you store heaps, you can use pointers. Each node at the heap could keep the element it stores, its key, and 3 pointers. But what's the difference between the element each node stores and the key?
Let me just double check this.
So this is heaps, because I thought we were just storing one number, which was like the key.
Each node at the heap. Oh, okay, right. I think this might be an Oxford comma kind of situation. You can interpret its key as being in brackets rather than enclosed by commas.
Okay. So just
yes, those are the same thing.
Okay, great. Just want to make sure. So sorry for the grand digression. I just want to be certain.
No, you're
Thanks.
Right. Okay, let me repin myself and yeah, okay. 12:45, so we've still got a bit of time. Any further questions that I can take?
Can I ask a assignment question quickly?
Okay, so people are asking about question 4 and question 1. Scroll up. Okay. I can take a question about the assignment, and then we'll see about question 4 and question 1.
Yeah, thanks. It should be pretty quick. I'm just not sure if it's possible for question 1 to run in ON time when we are comparing two indices in an array of n elements.
It's a good question, isn't it?
Yeah, I would expect to run n square.
You would expect it to run in n squared, right? If you were to check every pair of indices for whether they're consistent or not, then absolutely that would have to be n squared. So the intended solution is something that does not check every pair individually.
Right. So it is possible to run it.
It is absolutely possible, but it's not obvious, right? That's
Right.
why the questions are not just you loop twice and it's done. Yeah.
Okay. It's
But
interesting
there is
that
something clever that you can do.
it's interesting that part A is like ON and then part B is actually slower. I thought you were like difficulty will increase, gets faster and more optimized.
I would describe A and B as approximately equal difficulty. The point is not that one is better than the other, because the part A says expected linear time, part B says worst case log n log n time.
Yeah, that makes sense. I would just
So
get
a solution that satisfies the constraints of part A might not be a solution to B. So they are not like A is not a superset of B, if that makes sense.
Yeah, I will just use to the tutorial question. So if you look at tutorial question 1, which we're about to, that A
Yes.
is like O log n log n, B is expected ON, but then the
Yeah.
assignment flipped.
I guess the point is that ordering is arbitrary. It's not that one is a faster solution than the other.
Okay, yeah, thanks for the clarification. That's all I
Because
wanted to.
in all instances, except when we specify, we are asking about the worst case. Okay. So question 1. Describe an order n log n algorithm in the sense of worst case performance that determines whether two elements in S add up to X, and describe an algorithm that runs in linear time to do the same task. Yeah, so obvious parallels to the assignment question. Make of that what you will. Just make sure this is looking good. Okay, cool. That way. Okay. So I guess there is some thinking required before we can start writing things. We want to know whether pairs of array elements add up to X. And again, if we were to go through all pairs and ask, for all I, for all j, do they add up to X? Like, does S? Okay, let me write that down. The problem, of course, is that we are doing 2 nested loops, each of which runs through n steps. So this is quadratic time, and this is too slow. Yeah, so Kai is correct. The difference between expected case or average case are roughly the same thing, in the sense that quicksort runs in randomized quicksort runs in expected n log n, but the worst case is still n squared. So where an algorithm has a difference between where we are talking about the expected runtime of an algorithm, this usually indicates some kind of randomization. This is usually in the context of some randomization. Okay, so I hope that answers the questions in the chat. So as for question 1, we need to do something a little more sophisticated than just comparing every pair. And as we were discussing in the peer tutorial earlier, Kai's suggestion was, if we had this array in sorted order, then we would be able to search not comparing SI against every other SJ, but rather comparing SI and looking for the required value SJ to make it up to X. And we'd be able to do that efficiently. So let's have a look at how that pans out. first sort the array S using merge sort. Which runs in order n log n. Hopefully you're all familiar with merge sort from the lecture, if not from earlier courses. And then we need to go through this sorted array, and the point of and the benefit of sorting will be that we can search for a particular value in faster than linear time. So for each index I, we want to determine whether x minus s of I is an element of the array. Is that clear? Because in that case, that element together with Si will make up a total of X. And what am I doing? Okay. So how would we determine this? How would we look for the desired value X minus Si? If we are searching an array, which is a sorted array for a particular value, we can use what well-known algorithm?
Binary search.
Exactly, binary search. This can be determined in order log n time using binary search. Therefore, the main part of the algorithm runs in order n log n. Again, I don't think any further explanation is needed here. For each index I, of which there are n, we do log n amount of work. So this is n log n time. Why does binary search work here? Okay, great. So binary search lets us search a sorted array for a particular value in logarithmic time by saying we can test against the midpoint of the array and then recursing on either only the left-hand side or only the right-hand side. Yeah. Are you familiar with this idea? In this case, we are looking at the array S, which is now sorted, and we are searching for the value X minus Si. If such a value exists in the array, then together with Si, then the total will be X. So it's n log n plus log n. So we have to be careful here. This log n binary search doesn't just happen once. It happens for every index in the array. So that actually, so when I refer to the main part, I mean everything after sorting. So this is n log n to sort, and also n log n to, for every element, do a binary search. The big O notation hides constant multiples, as we will discuss in tomorrow's lecture, and therefore the total runtime of this algorithm is a big O of n log n. Okay. Now, there is a special case here, which I'm not going to describe just because of time reasons. You do need to be careful because, as I understand the question, it's not perhaps the most precisely written. We shouldn't include two elements which have the exact same index, that is, they're equal. You shouldn't count the same array element twice as adding up to x. So for example, if the number x over 2 or half x appears exactly once in the array, then we shouldn't count that element plus itself. However, if that array element occurs at least twice, then we could count it under two different indices I and j. So you should, so my understanding is you should write a special case that covers I think it's easiest to just handle this first. Check first whether the entry x over 2 appears at least twice in the array. If so, we are done. If not, we will just exclude, we will skip over that value when we get to the main part of the array. Or just delete that single value from the array altogether. Anthony suggests an improvement to this algorithm. It's a good idea. The idea is you can actually improve this slightly by always insisting that SI be the smaller of the two numbers, so that you don't then double count them. Now, this isn't necessarily a problem because my solution is only twice the runtime of Anthony's, and again, we aren't bothered about constant factors in this problem because it's hidden by the big O. So you could absolutely stop this, go through for each index I and stop if you get to x over 2, because at that point you are only finding the same pairs just the other way around. Yeah, so that would save you roughly a factor of 2, which in some practical applications might be relevant, but for the purposes of this course, we won't be talking about it. So the thing is that the problem was not to count the number of pairs. At least this problem was not, right? The assignment problem is. But this problem just said, is there a pair I and j that satisfies it? And so once we find one of them, we're done. In the assignment problem, you are required to count the number of pairs. And in that case, you do need to be mindful of whether you are double counting everything. Note, even if you are double counting everything, this is fine as long as you acknowledge at the end, oh, I have double counted everything because such and such reason, divide through by 2. That's a perfectly valid way to correct the double counting. Yeah, so Kai's suggestion is useful for part B of question 1. Instead of sorting, because that is now slower than we are allowed, you should put the array elements SI in a hash table and then iterate over that hash table and do a similar idea. If I find a value SI, check whether x minus SI is also a value in the array. And again, I can do that by looking up in the hash table. here we'll use the properties that insertion and lookup in a hash table run in expected constant time. So I hope that answers your question. Hash tables are prereq knowledge. You don't need to have a super clear handle on how exactly you would build a hash table in, your programming language of choice, but you should be aware of the idea, which is that using hashing, we can build these lookup tables that have expected constant time for insertion and for lookup. But of course, in a practical application, you do need to be aware of collisions, and that's why it's only expected and not guaranteed worst case constant time. All right, so we're coming up to time, so I understand that you guys may need to leave. If you have further questions, I'll stick around for a couple minutes, but then we'll wrap up. That's okay. I hope this has been helpful. Recording will be available on YouTube. I'll just mention that I do have the ability to stream on YouTube now, so we'll start doing that soon. Announcement will come out soon. Announcement will come out today. Okay, great.
I have a question.
Yep.
So, you know how I mentioned in the previous session about expected time, right? And you said usually it's like you need to reference or use another algorithm.
Yeah, that in this course that will usually be the case.
Yeah. So, is there how do we know? Do we just have to get from experience know the different algorithms that we could potentially apply?
Yeah, so you should it might be helpful for you to compile what the time complexities are for example, the algorithms that I've mentioned as the sorting and searching algorithms that I've mentioned as assumed knowledge, as well as some of the data structures and the key operations of those. So for example, you would include under hash table, lookup in constant time, insertion in constant time, or expected constant, sorry. Or for a binary search tree, you would include insertion in logarithmic time, lookup in logarithmic time, find max, find mean in logarithmic time, in constant. Sorry. What am I talking about? I guess you can, with some additional work, you can maintain those in constant time.
Yeah.
So yeah, you would, I think you would find it helpful to compile some sort of reference for this, but that's about all that I could recommend on this front. Otherwise, I'm sure that many algorithms textbooks and stuff not so much the textbooks for this course, because they'll probably assume those data structures. Maybe CLRS, I'm not sure. But earlier textbooks may well have references of this form that you can look up. Yeah. I hope that's helpful.
Okay. Yep.
Okay. Right. Any further questions? If not, I will wrap up here, and a reminder that the peer tutorial is running again at 5 o'clock today. And you can expect an announcement regarding future lectures and consultations today. All right. Otherwise, I will see you tomorrow in the lecture.